Swayam Prabha. Digital India. Educated India.
Now, I am going to discuss mathematical model for material removal in ultrasonic machining. Now, these models, there are various models that have been proposed by various researchers. For example, Miller proposed mathematical model for understanding the mechanics of cutting in ultrasonic machining in the year 1957. M.C. Shaw proposed a model for the same purpose in the year 1956. Then Kazantsev and Rosenberg proposed a model for understanding the mechanism of material removal in ultrasonic machining in the year 1965. And there are various other models which have been proposed and reported in the literature survey. However, I am going to discuss only one that was proposed by M.C. Shaw. Now, let us understand the mechanism of material removal as per the analysis reported by Professor M.C. Shaw. He made certain assumptions during the development of the model. As we see, he assumed that abrasive grains are spherical in shape and they are having constant diameter, that is small d, and equal to 2 capital R. However, in reality it is not so. The shape is not spherical and the size of the abrasive particles also not uniform, it varies within a certain range. Second assumption which is important to note is volume of the material chipped off from workpiece is equal to half the volume of a sphere of diameter equal to 2 small r. Here please note that this 2 small r is not equal to the diameter of the sphere, 2 r is something different as we can see. So, let us see the second assumption again, volume of the material chipped off from the workpiece is equal to half the volume of a sphere of diameter equal to 2 r. Note that here 2 r is not equal to d, because d is the diameter of the abrasive particle or the grit, while 2 r is the assumed diameter of the fractured volume considered as a sphere. As you can see here that this is the grit, and when it is penetrating up to this depth, it is assumed that the volume of this is equal to the semi sphere having the radius equal to 2 r. As you can see here, here is the tool which is vibrating ultrasonically, and here is the grit having diameter d, and this is the 2 r is the diameter of the hemisphere of the fractured volume. Side figure indicates clearly that capital R is equal to d by 2, where small d is the diameter of the abrasive grit, and at the bottom you can see small r is the radius of the hemisphere of the fractured volume of the material, and then other things h is the penetration to which the abrasive particle is penetrating inside the workpiece surface, and capital R minus h is the rest of the arm of this figure shown over here. It will be utilized for the calculation in the following slide. So, material removal by throwing mechanism and hammering mechanism, two of the mechanisms that have been considered. I will show you what do they mean In fact, in the following slide, as we can easily understand here, suppose this is the tool and here is the workpiece, and say this is the abrasive particle in the slurry. When this tool is vibrating ultrasonically, this will hit this particular abrasive particle. As a result of this, this particle will move towards the workpiece and penetrate inside the workpiece, as in this particular case or in this particular case. So, this is known as throwing model, because here particle is thrown by the tool towards the workpiece. In the second case, this is the workpiece, this is the tool, and if the gap between the bottom face of the tool and top face of the workpiece is smaller than the size of the abrasive particle, then this tool will be hitting the abrasive particle, and part of the abrasive particle will penetrate inside the tool, part of it will penetrate inside the workpiece, and this is known as hammering model. Other modes of material removal like cavitation and chemical action of the slurry on the workpiece are neglected in this particular model. Radius of the crater formed due to fracture R, as I have shown in the figure in the earlier slide. Here crater is assumed to be hemispherical, as shown over here with the dash line. Radius R in terms of abrasive particle radius and depth of penetration is small h, as I have shown earlier. They can be expressed like R square is equal to capital R square minus within bracket R minus h whole square, and this is very clear from the previous slide where the figure is shown. So, R square and R square will cancel, we are left with 2 R h minus small h square here, and this comes out to be approximately equal to 2 R h. Here h is the depth of penetration, as you can see here this, and this is very small, and the square of this depth of penetration h square will become still smaller, hence it can be neglected. Now, let us find out what is the volume of material removed per grit per cycle, and let it be expressed by Vg. Now, this Vg will be equal to half of the volume of the sphere. Now, here as you can see, we have assumed that this is the semi sphere. So, actually this is the sphere. So, half of the volume of the sphere, the volume of the sphere is given by 4 by 3 pi r cube, and half of it becomes half multiplied by 4 by 3 pi r cube, and this comes out equal to 2 by 3 pi within bracket 2 r h raised to power 3 by 2. And here as you can see in the previous line, we have shown that r is equal to approximately 2 r h. So, if we take this one, then we get this equal to k 1 h into d whole raised to power 3 by 2 millimeter cube per grit per cycle. This is the volume, where k 1 is the constant which can be evaluated by the experimental results. H and d are to be given in millimeter. Here h is the depth of penetration, as has been shown over there. Now, let n be the number of impacts per cycle, where n is an inverse function of cross sectional area of the grit, and whose diameter is d. Now, let us see here two figures. On the left side there is a abrasive particles of the smaller size having diameter d, and on the right side you have the abrasive particles of the larger size. Now, as you can see, larger the size of the particle, larger number of the abrasive particles are covering the same area. So, you can write n is equal to K2 by or K2 upon d square, where K2 is a constant of proportionality. Now, is every grit active? This is the question which arises, as you can see here in the figure. Suppose this is the tool and there are various abrasive particles. Whichever particle is hit by the tool, the question is whether every particle is reaching to the workpiece and hitting the workpiece, or some of them are just dying out their energy dies out while travelling from the tool towards the workpiece. So, what it is done, let K be the probability that a particular grit under the tool is active or it is hitting the workpiece and removing the material. Then the volume Vc is the material removed per cycle, can be given by K multiplied by Vg into number of impacts, which becomes equal to K multiplied by K1 into K2 Hd raised to power 3 by 2 divided by d square, that comes out to be equal to K into K1 into K2 under the root H cube by d. Now, here we have substituted the value of Vg that was found in the previous slide. So, volumetric material removal rate MRRV is equal to K K1 K2 multiplied by F under the root H cube by d, and this unit is cubic millimeter per second. Now, here we can see it is multiplied by F, where F is the frequency of vibration of the tool, and here you can see you can determine K, K1, K2 from the experimental results. F is already known, that is the frequency of vibration, and d is the diameter of the grit, which is also known, but we do not know the depth of penetration H, that is given over here. So, we will be using two different models. The question arises how to know the depth of penetration. There are the two models proposed by the Professor M.C. Shaw. One is the throwing model, another is the hammering model, which I have already explained to you. This is the throwing model and this is the hammering model, or this is the throwing model and the hammering model. As you can see clearly, the tool is thrown by grit is thrown by the tool and it is penetrating inside the workpiece. FTH is the force acting when the tool is hitting the abrasive grit in the throwing model. A grain is thrown onto the workpiece by the tool, as we have already seen in the slide, and this is very clear from the slide on the figure on the right side, and we can see t is the time that is equal to 0, that means when time is 0, the tool is just touching the abrasive particle. Now, the motion of vibration can be expressed, or the displacement can be expressed as by is equal to a by 2 sin 2 pi f t, where we already know that a by 2 is the amplitude of vibration, f is the frequency of vibration, and t is the time at which we are trying to find out the displacement. Now, velocity of tool can be evaluated by dy over dt, that is equal to y dot, and if you differentiate the earlier equation, it comes out to be by a f cos 2 pi f t. The maximum velocity that a tool can achieve is given by y dot maximum equal to pi a f, and this will be maximum only when value of the cos 2 pi f t is equal to 1. So, for cos 2 pi f d is equal to 1, we achieve y dot maximum is equal to pi a f. Now, here there is a very important assumption in while determining the maximum velocity of the grit particle or the tool, especially when we are assuming that the grit also leaves the tool at this particular maximum velocity at which the tool is vibrating. This tells the tool vibration, where amplitude of vibration and the time both are shown. Now, from this we can find out the kinetic energy contained by the abrasive particle. We already know kinetic energy is given by half m v square, while m is the mass of the abrasive particle, v is the velocity of the abrasive particle with which it is moving towards the workpiece or it is hitting the workpiece. And as you can see here, the mass is given by pi by 6 d cube rho a, where rho a is the density of the abrasive particle and small d is the diameter of the abrasive particle, and pi square a square f square is the v square or the maximum velocity of the abrasive particle with which it is hitting the workpiece. Now, full kinetic energy is absorbed by the workpiece before the particle comes to rest, it is assumed. It will result in penetration equal to h T h w. Suffix T h w or subscript T h w indicates T h stands for throwing model and W stands for workpiece into the workpiece. Then the average work done is given by half f h T h w, where h we can determine from the figure. As you can see here, it is assumed that the variation in the force is triangular in nature, assuming that the force variation during penetration is triangular in nature. Average contact stress sigma w on the work surface is equal to brittle fracture hardness of the workpiece material. With this assumption, sigma w is given by f divided by pi h T h w d. Now, here pi d h T h w. Just a minute, h T h w. Now, this portion pi d is the periphery of the spherical hemispherical penetration that we are assuming, and this gives the this gives the h T h w. So, from this we can find out whatever is the area over which force F is acting. From there we can determine the sigma w. So, we get F is equal to pi h, this will be pi h T h w d h, substituting sigma w is equal to h. It is known that kinetic energy of a particle is equal to the work done. So, we can equate the work done to the kinetic energy of the abrasive particle. So, we can see here half m v square is equal to half pi upon 6 d cube rho a multiplied by pi square a square f square is equal to pi h small h d h T h w. Now, if we simplify this equation, we get the value of the h T h w is equal to pi a f d multiplied by under root rho a divided by 6 capital H. Now, from here one can determine the depth of penetration in the throwing model in the workpiece, and this value can be substituted in the value of, in the equation which we initially this value of h T h w from equation 3 can be substituted in the equation 1 derived for evaluation of MRR V T h, where V T h is volumetric material removal rate in throwing model by the throwing model. In the same way, H can be derived if the material removal takes place due to hammering action as follows. This clearly indicates how the hammering model is going to work and what is happening in the hammering. As you can see here also, part of the abrasive is penetrated inside the tool and part of it is penetrated inside the workpiece. Now, here it indicates the tool, the topmost position of the tool where from it starts vibrating, mean position of the tool and bottommost position of the tool, and at the bottommost position of the tool it is hitting the abrasive particle or hammering the abrasive particle. Now, it is assumed that the grain is hammered into the workpiece as shown in the above figure. It simply means that the gap between the bottom face of the tool and top face of the workpiece is smaller than the size of the grain, that we can see here. This is the size of the grain and this is the bottom face of the tool and this is the top face of the workpiece. So, tool will hit the abrasive particle only when this gap becomes smaller than the size of the abrasive particle or the grit size. Mean speed of the tool is quite low. Mean static feed force is applied to the tool and it is expressed as F, and this is equal to mean force of tool on the grit. Delta T is the duration of impact. Fi maximum is the maximum value of impact force Fi, which is acting on the abrasive particle. Force will vary with the depth of penetration by the grit. Exposed contact area between the grain and workpiece are different and grain and tool is also different. This indicates the delta T indicates the period during which abrasive is in contact with the tool and workpiece both, and capital D indicates the cycle time. This average force in this particular situation can be evaluated with the help of this equation. F average is equal to 1 upon T integration 0 to T Fi T dt, where T is the cycle time. Now, there are various positions of the tool during a cycle. You can see here top position of the tool, which is indicated by C, mean position of the tool is indicated by O, when tool touches the grit is indicated by A, and bottom position of the tool is indicated by B, and workpiece is shown over there, tool are separately shown there. The cycle time is capital T and the time required for moving from O to B is T by 4, and the time during which abrasive and tool and workpiece are in contact with each other is delta T. The movement from A to B is due to impact on the abrasive particle. As the tool touches the abrasive, it experiences the resistance to move. Let us assume nature of variation of force Fi as triangular. So, you can see here Fi maximum is the maximum force which is experienced by the abrasive particle. Fi is the force and delta T, as I have mentioned earlier, is the period during which abrasive, tool and workpiece are in contact. Due to this force, the abrasive will partly penetrate in the tool and the depth of penetration is H suffix Th, and partly in the workpiece, and it is expressed as H suffix Wh, where W stands for workpiece, H for hammering model. Total indentation Hh during hammering is given by the sum of the penetration in the tool and the workpiece, and it can be expressed as H H is equal to H T H plus H W H. This is very clear from this figure. H T H is the penetration depth inside the tool and H W H is the penetration depth inside the workpiece, and force F is acting on the grid particle. Average velocity during the quarter cycle OB is given by A by 2 divided by T by 4. T by 4 is the time taken in the quarter cycle and A by 2 is the amplitude, and this is given by 2 A by T. If delta T be the time required to travel from A to B, that is approximately total penetration depth H H, then delta T is equal to H H, that is the total depth of penetration, divided by the velocity, that is given by 2 A by T. So, we can simplify this. H H is equal to H T H plus H W S multiplied by T divided by 2 A. Now, here let F average be the average force acting during one cycle, then F average can be written as 1 by 2 F I maximum multiplied by H T H plus H W H multiplied by T by 2 into A and divided by 1 by T. Here you can see, since there is a triangular force variation that we have assumed, so the average will be the, this is the F maximum and here is the 0. So, average will be F maximum divided by 2, that you can see the first term, and H T H plus H W H multiplied by T divided by A 2, that gives you the time delta T during which this force is acting, and T is the capital T is the cycle time. So, this will give you the average force, or you can write it like this: F I maximum is equal to 4 F average multiplied by A divided by H T H plus H W H. Now, maximum force per grid will be obtained when the total force that is acting on the tool is divided by total number of particles which are being hit by the tool. So, let this be the capital N as the total number of abrasive particles which are being hit by the tool. Now, what is going to be the maximum stress developed in the workpiece, because abrasive particle is in contact with the tool as well as the workpiece. So, and depth of penetration in the tool as well as workpiece are different. So, the area on which the force is acting will also be different. So, the stress is developed in the tool as well as the workpiece will be different. Let us find out the maximum stress developed in the workpiece. It is given by sigma suffix W is equal to F I maximum divided by N multiplied by 1 over pi H d by pi d H W H. The term within the bracket gives you the area. Same way you can find out the maximum stress developed in the tool, that is sigma T is equal to F I maximum divided by N within bracket 1 over by pi d H T H. Now, substitute the value of F I maximum in above equation A, then you get the stress sigma W in the workpiece, that is 4 F average A divided by H T H plus H W H multiplied by 1 over N pi d H W H. Assumption here made is as follows: number of grids acting is inversely proportional to the square of the diameter for a given area of tool face. I have already shown one slide regarding this, and we have already seen, then N becomes proportional to 1 by d square, and K2, this becomes equal to K2 divided by d square, where K2 is the constant of proportionality or you can write down sigma W is equal to 4 F average A D divided by H T plus H W into K 2 whole of it multiplied by 1 over pi H W. Now, you can further simplify it and you get it as H W square is equal to 4 F average A D divided by sigma W pi K 2 within bracket lambda plus 1, where lambda is equal to H T over H W and depth of penetration will be inversely proportional to the strength of the workpiece or the tool. If higher the strength, lower will be the depth of penetration. That is why you can see here H T over H W is equal to sigma W over sigma T. Stress sigma W can be replaced by bindle hardness number H. Both are the same, sigma W is equal to H W, that is the workpiece bindle hardness number. Above equation can now be simplified as H W square is equal to 4 F A D square divided by pi K 2 C D H W within bracket lambda plus 1. Substitute the value of H W in the equation rate by hammering model comes out to be equal to K K 1 K 2 multiplied by the term given over here 4 F A divided by pi K 2 C D H W within bracket lambda plus 1 bracket closed whole raised to power 3 by 4 into D raised to power 1 by 4 multiplied by F. I have already mentioned F is the frequency of vibration. Now, from the theoretical, okay, let me go back once again. Here one point you have to note that the volumetric material removal rate is proportional to D raised to power 1 by 4, but practically it is observed something different rather than D raised to power 1 by 4. I will explain it later on. From the theoretical calculations, it has been found that material removal rate in throwing model from throwing mechanism is much smaller than MRR VHM, that is the volumetric material removal rate from hammering model, and it is many times so small compared to hammering model that it can be neglected. The discrepancy is observed between experimental and theoretical results. Theoretical results calculated by Shaw's model, lot of discrepancy was observed with the experimental results. Then later on Professor Shaw tried to explain them the discrepancies as follows. What he considers that actual shape of the grain is not spherical and they are not smooth also. Now, I had mentioned this particular point earlier also, and they have projections of average diameter and he assumed that it is equal to d 1 and d 1 is proportional to d square or d 1 is square is equal proportional to d raised to power 4, but MRRV is proportional to d raised to power 1 by 4. So, if we substitute there the value of this in the hammering model, then we get d raised to power 4 whole raised to power 1 by 4, you get proportional to d, and experimentally it is observed that volumetric material removal rate is proportional to d. As F increases, MRRV also increases. In practice, beyond a certain value of F, it starts decreasing because abrasive grit gets crushed under heavy load. As F increases, MRRV also increases. In practice, beyond a certain value of F, that is the force, it starts decreasing because abrasive grit gets crushed under heavy load. Now, let us take one example to understand how the forces etc. can be calculated. Find out the approximate time required to machine a hole of diameter equal to 6 millimeter in a tungsten carbide plate whose fracture hardness is equal to 6900 megapascal and it is of thickness equal to 1.5 times of hole diameter. The mean abrasive grain size is 0.015 millimeter. The feed force is equal to 3.5 Newton. The amplitude of tool oscillation is 25 micron and the frequency is equal to 25 kilohertz. The tool material used is copper having fracture hardness equal to 1.5 into 1000 Newton per millimeter square. The slurry contains 1 part abrasive to 1 part of water. Take the values of different constants as K1 is equal to 0.3, K2 is equal to 1.8 millimeter square, K3 is equal to 0.6 and abrasive density equal to 3.8 gram per cubic centimeter. Also calculate the ratio of the volume removed by throwing mechanism to the volume removed by hammering mechanism. This problem has been taken from the book Advanced Machining Processes published by IIT Publishers. This problem, to solve this particular problem or before solving this particular problem, let us see what are the available data. Hole diameter is equal to 6 into 10 raised to power minus 3 meter. All the data that are given have been converted in meter. So, that is why you can see here plate thickness is equal to 1.5 into hole diameter, that comes out to be 9 into 10 raised to power minus 3 meter. Mean abrasive grain size, it should be grit, not the grain. Mean abrasive grit size is equal to 1.5 into 10 raised to power minus 5 meter. Feed force is equal to 3.5 Newton. Amplitude of tool oscillation is given by 25 into 10 raised to power minus 6 meter and frequency of oscillation is 25,000 cycles per second. Fracture hardness of workpiece material, that is sigma W is equal to H W is equal to 6.9 into 10 raised to power 9 Newton per meter square. Fracture hardness of tool material, that is H T is equal to 1.5 into 10 raised to power 9, not 109, this is 10 raised to power 9 Newton per meter square and abrasive grain density rho A is equal to 3.8 into 10 raised to power 3 kg per meter cube. So, the value of the lambda can be found equal to can be written as lambda is equal to H W divided by H T, that is equal to 4.6, K1 is equal to 0.3, K2 is equal to 1.8 millimeter square and that comes out to be 1.8 into 10 raised to power minus 6 meter square and K3 is equal to 0.6 and C is equal to 1. Here C is nothing but the concentration. The following procedure should be adopted to solve the problem. First, we should try to find out what is time required to machine the hole. We know that the volume of material removed using ultrasonic machining can be calculated using the following relationship, that is V is equal to K1 K2 K3 under the root H raised to power 3 divided by D into C F. First step to be followed in the solution of this problem is calculate the value of H, which is different for throwing model, that is HTH, and for hammering model, that is the HWHM. Step 2, after knowing the values of HTH and HWHM, calculate VTH, that is the volumetric material removal by throwing model and volumetric material removal by hammering model from the workpiece by substituting these values in above equation 1. Then find the total volume of material removed per unit time by adding VTH and VWHM. In the third step, calculate the total amount of material to be removed to make the required hole. Divide this volume by Vs that has been calculated in the earlier step 2 to find the total time required to make the hole. In step 4, find the ratio of HTH divided by HWHM. Following the above steps, all calculations are made as follows. In step 1, in equation 1 except h all other parameters are known. Let us calculate the value of h t h by throwing model, and the equation is given as follows. Now, let us substitute the value of pi a f d sigma a and sigma w rho a and sigma w as follows, and we get h t h equal to 1.78 into 10 raised to power minus 5 millimeter. So, penetration h w h m in the workpiece due to hammering is given by the following equation, that is h w h m is equal to 4 f average a d divided by pi k 2 sigma w multiplied by within bracket lambda plus 1 bracket close whole under root. Substitute the values which we have already given in the earlier slides, and we get h w h m equal to 2.192 multiplied by 10 raised to power minus 4 millimeter. Now, volume removed by throwing mechanism is given as follows. This particular equation is to be used for the throwing model that we have already derived, and if we substitute the values of various parameters, we get that the volume of material removed by throwing model equal to 4.97 into 10 raised to power minus 3 cubic millimeter per second. Now, volume removed by hammering model can also be found in the same way. This is the equation which we have already derived. Substitute the values of various parameters and constants, then we get volume of material removed by hammering model is equal to 0.2146 cubic millimeter per second, which is much higher than what we get the volume of material removed by throwing model. So, what is the time required to drill a hole? As I have mentioned earlier, that the volume of the hole to be drilled divided by the volumetric material removal rate by both the models, hammering model as well as throwing model, that will give you the time required for drilling the hole, and this is, as you can see, values have been substituted here and you get 19.289 minutes. We can also find out the ratio of VTH and VWHM, and by substituting these values of VTH and VWHM, we get the ratio as 0.023. Thus, from this value of 0.023, it is evident that the material removed by hammering is much more than by throwing, approximately 43 times. Hence, for approximate calculations and for all practical purposes, volume removed by throwing model can be ignored as compared to the volume of material removed by hammering model. This way you can make the calculations for various types of the problems given in the examination or in the practical life. I have tried to give a question bank also, and these problems you can solve at your convenience. I have given various problems over here, as you can see, and for solving these problems, you can take the help of both these lectures as well as you can take the help of the book which I have already mentioned to you. Thank you very much.